Yeah, okay, guys. So let's quickly look at energetics. So energetics is actually a very interesting topic in chemistry, and it's actually a nice one. So we are going to dive dive deep into energetics and then look at some cool stuffs. So let's move. So since it's energetics is about chemical reaction, and we already know what the chemical reaction is, so let's just quickly remind ourselves of some stuffs so we can just keep up with the class. So chemical reaction is a process that changes some chemical substance to others. Yeah, the chemical reaction is a chemical change that form new substance. You know that already. So a substance that starts a chemical reaction is called a reactant. Then the product is what is a product. So then during chemical reaction, the reactants are used up to create the product. Yeah, we use the reactant to create product. So reactants are disappearing, products are appearing. So another example of a chemical reaction is the burning of methane gas. So in this chemical reaction, the reactants are methane and oxygen, and the product of what CO2 and water. So you may not quite understand that, but just know that CH4 plus O2 is giving us what CO2 and water. That's a chemical reaction. So as this example shows, a chemical reaction involves the breaking and forming of chemical bonds. So chemical bonds are forces that hold together the atoms of a molecule. Bonds occur when atoms share electrons or maybe transfer or all this kind of stuff. Then when methane bonds, for example, bonds break within the methane and oxygen molecules and new bonds forms the molecule in carbon dioxide and water. That just to elaborate the definition we have up there. So the role of energy in a chemical reaction. Yes, why do we need energy? Because this topic is energetics. So it's just talking about the energy in what's in a chemical reaction. So matter rusting or burning are example. Matter rusting basically, don't forget, it's only iron that can rust. So, I wanted to add that actually. But you can just say matter corroding or burning. So, corrosion is for all metals, but rusting is particularly for iron because the word rusting means formation of rust, and rust is an iron compound. Shey you get. So sodium will tarnish, sodium will not rust. Shey you get. Aluminium will not rust. But sodium, instead of rusting, you see what's tarnishing. Yeah. So no matter rusting or burning are common examples of what chemical changes. So chemical changes involve chemical reaction in which some substances called reactants change at the molecular level to form the substance called product. Okay, all chemical reactions involve energy. However, not all chemical reactions release energy, as rusting and burning do. In some chemical reactions, energy is absorbed rather than released. Yes, some chemical reactions are just kind of there in a way such that for them to occur, you just need to add energy to them. That's it. While there are some that normally they can occur without anything, like they are spontaneous, they can occur without you adding energy to them. In fact, when they are occurring, they still give out energy. Like we are so rich, we have a lot of energy in us. Let's give it out. Do you get my point too? When you put them together, they just start occurring. They start reacting, and they still give out energy. Shey you get. So some reactions were taking energy, some reaction give out energy. Shey you get. I know you know what the ones that give out energy is, but we are still going to look at those as we move on. Okay, so moving on. So enthalpy, what's enthalpy? So I want to discuss some key notes we need to get here. So enthalpy, so this is the total heat content of a reaction. Yes, enthalpy is the total heat content of a reaction. If you have the enthalpy of combustion, that means you're having a combustion reaction. Then the heat content of that reaction, of that combustion reaction, is the enthalpy of that reaction. So you get. So enthalpy is significant because it tells us how much heat is there in the system. Yeah, in form of energy actually. Then heat is essential because it allows us to produce useful work. Yes, it is from the energy enthalpy that you now get out your useful work, your useful energy, the energy that you use to do the work, that you use to convert your reactant to product. That's the idea. So the absolute enthalpy has a state function. A state function is a function that, okay, maybe for example now, I can just say that my age is 79. You can argue that I'm actually 79. So I can tell you that my age is 79, and that's like you don't need to start checking where I started and where I am. No, it's just like something you can get now. I can tell that my weight is this. Shey you get. That's the idea. So enthalpy, absolute enthalpy is just like, okay, you look at the system and then you measure that enthalpy. Yes. So it is not easy to measure the enthalpy of a system. Same thing with entropy and the likes. But we can get the change because when your reactant is changing to product, it is either they lose or gain it. She gets so when they lose it, we can know what they lose, and that thing that they lose will be their change. She get my point. And whatever they gain to that thing they gain will also be the change. So that's why you can only get the change in entropy, change in entropy, change in gives you energy, but you cannot get the absolute values of those guys. So when energy enters or leaves a system in form of heat, then we can conclude that the heat that leaves or enters will be the change in the enthalpy of that reaction. That's it. Sometimes referred to as the heat content. Enthalpy is a fascinating and uncommon word that most people prefer to use. I mean, enthalpy is sweet. Okay, good. So gives free energy now. So that's the useful energy of a system. When you hear the word gives free energy, that is the energy the reactors are using to get what to product. Without the gives free energy, nothing is happening. She gets. So gives free energy is a state function and an extensive property. Since change, though the gives energy is a state function, but the change in gives free energy is what is a part function that you need to get it. Is it like you are getting the change? It depends on two states. She get a quantity that depends on two states is a part function. She get that's just the idea. If you don't get it, you can raise the discussion on the group. We are going to discuss that. So since change in enthalpy increases or decreases, the randomness by affecting the molecular motions, entropy change alone cannot account for the spontaneity of a such process. So therefore, we use the Gibbs free energy for explaining the spontaneity of a process. Spontaneity means will this reaction occur? Will it not? So the expression for the Gibbs free energy will be like delta G equals to delta H minus T delta S, where delta G is what the Gibbs free energy, and that's the useful. The delta H is the what enthalpy change, which is what total heat content. Then the temperature is in Kelvin, of course. And then the entropy change, which is what the degree of disorderliness of the system, how the particles in a system are moving up and down. That's how you can say your boiling water has higher entropy than your maybe cold water. She get that's exactly about that. Then the old of T delta S is what the useless energy. So if delta H is the useful energy, and if delta H is the total energy, and you now subtract the useless energy out of it, what are you going to get? The useful energy. That's how delta G is a useful energy. So what's entropy now? So the degree of disorderliness. That's just it. So entropy is one of the important concepts that students need to understand clearly while studying chemistry and physics, of course. More significantly, entropy can be defined in several ways and thus can be applied in various stages of or instances such as in the thermodynamic stage, cosmology, and even economics. The concept of entropy basically talks about the spontaneous changes, talks about the spontaneous changes that occur in the everyday phenomenon or the tendency of the universe towards disorder. Generally, entropy is defined as a measure of randomness or disorderliness of a system. That's just the idea. So I don't want to take it so deep. Entropy is very, very deep. You can start calculating, but for your level, entropy is basically the measure or the degree of randomness or of a system. So let's now talk about endothermic and exothermic reaction. Yes, you might have guessed this right. So for an endothermic reaction, is a reaction where heat is entering a system, while exothermic is what where heat is leaving the system. So that means you can actually take this in many ways. For let me just take endothermic, then the opposite will be for exothermic. So for endothermic reactions now, you can say it's a type of reaction where the the system now, that which is the reaction, is gaining heat from the what from the surrounding, or you can say is a kind of reaction where the surrounding is losing heat to the system. Shey you get? So it depends on how you are taking it. Then exothermic will now be the reverse, where the surrounding is absorbing heat from the system, or the system is losing heat to the surrounding. That's just the idea. So a popular example of an endothermic chemical reaction is photosynthesis. During this process, plant absorbs energy from the sun and converts it to carbon dioxide. They absorb energy as endothermic. And water into glucose, blah blah blah. Example of an exothermic reaction is one between sodium and chlorine producing a bright yellow light and a great amount of heat energy. So those are still basic. So moving on to the next. So exothermic and endothermic, okay, this is just a picture showing that okay, this is the system, it's losing it to the surrounding. This is the system, it is gaining it from the surrounding. That's just it. So for endothermic reactions now, so for an endothermic reaction, so an endothermic reaction is a term that describes a reaction where the system absorbs the energy from its surrounding in the form of heat. A few example of the endothermic process are photosynthesis, endothermic shey get photosynthesis, because it's also getting sun light energy, evaporating liquids. Before you can evaporate a liquid, you must heat it, you must add it to it, melting of ice, all those guys. Shey get the reverse will be the other way around. Then, as the name implies, endo means to absorb and thermic means heat. So the energy is produced as a result of reaction of reactant into the product. It occurs as a result of dissociation of bonds between the molecules. The energy is then released through the formation of new bonds. It is taken up from the surroundings in such reactions, so the temperature of the system where the reaction is taking place remains cooler. Also, the at the end of the reaction, the enthalpy, which is the change in heat energy during the conversion of reactant to product, increases, is a positive value. So for your enthalpy, the enthalpy for an endothermic reaction is a positive value, while the enthalpy for an exothermic reaction is what? A negative value, because it's going to what? Reduce. Yeah, it's going to decrease. So I think I've explained all this before. So the thermal is okay, good. So that's just that about that. So the exothermic, let me see if there's something we need to just elaborate. The exothermic reaction is the opposite of endothermic. Okay. It releases energy by light or heat to its surrounding. It gives energy out. So a few examples are neutralization, burning of a substance. All combustion reactions are exothermic. Reactions of fuel, deposition of dry ice, respiration. Yes, respiration, because you're actually what getting energy from it is going to reduce energy for the system, for the body to use. So solution of sulfuric acid into water and much more. So the energy release is caused by the formation of new bonds. Yeah, formation of bond is what? Exothermic. Breaking down of bond is what? Endothermic. Please note that it's a very popular question. At a higher level, why the energy required to break up the bonds is lower. At the end of the reaction, the enthalpy change decreases as well. That's just the idea here, because the reactant are losing energy to form the product. So you get that means the product will have lower energy. When I say the energy of the product minus that of the reactant, you are going to get a negative value. And that's just the summary of everything there. So the difference between the two now. So endothermic reactions are reactions in which, okay, they absorb heat, while this one they release heat. The energy is absorbed from the surrounding into the reaction. The energy is released from the system to the what? Environment. Energy is in the form of heat. Energy is released as heat, electricity, light, or sound. Yes, just that, please. Then melting, these are just the examples. Okay, so energy profile of the chemical reaction now. So with energy profile, although these are just a bonus, but you will understand better what we have been discussing. So energy changes can be represented using energy profiles. So catalysts including enzymes speed up chemical reactions. Although let me just correct that immediately. We don't really say they speed up, sure you get. They don't like really speed because we also have negative catalysts. That's one thing to note. There are negative catalysts. Because I'm trying to just change that immediately. Speed up or slow down, or you can just say alters the rate of get chemical. That's just the idea there. So your catalyst now, they can either speed up or slow down depending on what they are doing. Yeah. So for chemical reaction to occur between two particles, they must collide enough with each other. The minimum energy of the minimum amount of energy needed by particles when they collide in order to cause a reaction is called the activation energy. Before the reactant can be converted to the product, they need to have a particular energy that is called the activation energy. Some people can say that the activation energy is a barrier. Yes, before you can jump over a barrier, you must have the energy that the barrier is having. Shey you get my point? So the energy you now need for you to be converted to product is the activation energy. You need to overcome that energy. Shey you get? So your catalyst can now even increase that energy, that make the energy more, or even reduce the energy. Shey you get? So when they reduce the energy, that means you need lower energy to just be converted to product, and it will be faster that way. That's just the idea. So an energy level diagram shows whether you are, this is on its energy level. I'm trying to just compare energy level and what energy profile. So shows whether a reaction is exothermic or endothermic. It shows the energy in the reactant and the product, then the difference in the energy between them. So look at this now. So we have the reactant here, we have the product here. Look at the energy of the product. It was lower compared to that of the reactant. That means energy is released. Do you get that? So what for the other guy now, see reactant and product, it is up, right? That's just the difference between the two guys. But now, let's now come to energy profile now. So energy profile is kind of going to show us our activation energy and everything. So looking at this green, the energy that is absorbed and released here, that's the enthalpy change already. Sure you get, but we are not seeing the activation energy here. So let's look at this. It is usually more helpful to describe how the energy of a chemical changes during of chemicals changes during chemical reaction. So a reaction profile is more useful than an energy level diagram. A reaction profile includes the activation energy, which is the minimum energy needed. This is evolution now. Minimum energy needed by particles when they collide for a reaction to occur. The activation energy is shown as a hump in the line. Yes, as a hump. Like you see the hump now. And it starts as the energy level of the reactant and is equal to the difference in the energy between the top of the hump and the reactant. So let me show you that. So this is the hump they are talking about. This is the hump. Shey you get. So it starts at the energy of the reactant, and then it is equal to the difference between this health level and the energy of the reactant. That's the activation energy. So this is for an exothermic reaction. So I would love to give you guys an assignment on this, that draw for that of what? Endothermic reaction, yes, and explain everything. So the overall change in energy is what now? That's the enthalpy change. This is the product, this is the activation energy, and this is what? This is the reactant. So you, in fact, you cannot even say for the reverse, for the backward reaction, the activation energy will be everything here. Yes. So what we are going to do now is, in the next class, maybe when we are treating chemical equilibrium, we are going to discuss more on reversible reactions. So yeah, let's take care.